is sort of funny, but we're going to try a Padlet on the side as we're doing the lecture. And then if you have questions and you don't want to raise your hand, you can, in the Padlet, you can ask me questions. So there is a link in your Weber Canvas to the Padlet, and the password to get into it is questions. So if you'll just get that up, that would be awesome. We are going to, not today, I forgot, you don't need Davis ones up, but we'll be using the Davis site to use some Nearpod, because the Nearpod is paid for by Davis School District, but it's not paid for by Weber Weber State. So I'll be taking you there to help you do some review with Nearpod. But right now we'll just use the Padlet to get going. So remember go to this, click the link, and then the password is questions with a capital Q. Let me put that down. I think we ended at 14, or were we past 14 on the slide? Did I have you guys write down where we were at?
We just finished.
So we did the whole thing, this whole thing right here? Did we do this one? So we're right here? Okay. So we're going to start right there. Thank you. So exceptions to the octet rule. So I'm going to have this up and I'll just glance at it. So if you have questions, I'll have it here and you won't have to raise your hand if you don't want to. Yes, ma'am.
Okay, so I don't have access to the text anymore, so I dropped this class with Marin and the text so
Because you dropped this class? So where are you supposed to be then?
I don't know, because I dropped it on Weber, but it's like still on my work schedule.
Yeah, because if you dropped it, you can't be in here because it's a pure class.
Okay, can I run into it?
Yep. Yes? It should be in the front of the CE Chem 1110. Okay, so what we're going to do, sorry, my thing went to, we're going to talk about the exceptions to the octet rule. So here's our exceptions. Boron is an exception. Boron only has 3, and when it bonds, it doesn't have that 4th room open. Remember, we talked about the 4 rooms around. So it can only have 3. So when boron bonds, the maximum it can have, like I said, is 3. So we have a fluorine come here. We'll have a fluorine come here. That extra, I don't know where, that extra line there is not supposed to be there, but it's showing. And the one right here. And that's how we would show boron trifluoride. Okay? I want you to try and do boron trihydride, which is that one next to it, which will be basically the same, only change out the fluorines for hydrogens, and you won't have to do all the extra dots. Then we'll talk about the 2 at the bottom. So boron is one that doesn't make it to 8. The ones on the bottom, P.S. by the way, they get it their way. Okay, hopefully you were able to just write the boron, do a hydrogen, and do a hydrogen, and you're done. This shape is known as trigonal planar. It will stay in the plane and it will make a triangle shape. Okay, so pretty easy. The bottom 2, P and phosphorus and sulfur, these ones do something funky. I'm going to do sulfur, but I'm going to have you do phosphorus. Watch what I do with sulfur. Sulfur, if we put all the dots on it, has a total of 6. Everybody okay with that? Now, I sort of call phosphorus and sulfur, P.S. by the way, they get it their way, the party animals of the periodic table. The more the merrier. They will split up and do whatever they want to do to get as many as around them as possible. So basically, it will share each individual with a fluorine, each individual element with our electron with a fluorine, so it has as many around it as it possibly can. So what actually happens, this becomes really hard to see what kind of shape this is going to be. So if I draw it a little bit differently, sulfur's in the center, there'll be a fluorine up top with its 6, a fluorine on the bottom with its 6. And then what happens is on a plane in the center here, these fluorine come like this. Now, it's still a little hard to look at in this shape. Let me finish drawing this and I'll show you another shape really quick. It's basically if I took a square piece of paper and stuck a pencil down through the center of it, that's the shape that it would be. We call it octahedral. Okay? So it does a funky thing. Okay? I want you to now do phosphorus and try and figure out what kind of shape it might want to go. Did you get a notes thing? You don't know where it is. If you need to go grab another one, do. Yep. Okay, hopefully you were able to say, okay, phosphorus had 5 around it. And each of those chlorines going to come in and grab one. And the chlorine's going to have 6 other electrons that aren't shared. And we really can't leave it like this because we're not supposed to just pull the numbers or pull the things out. But at least that gives me an idea what it's supposed to look like. And I can say, okay, phosphorus is going to be in the center. It's going to have a chlorine that comes out at the top. It's going to have a chlorine that comes out of the bottom. And the other 3 need to be on the same plane. So this would be like cutting a triangle piece of paper and sticking a pencil through it. Like this. This is called trigonal bipyramidal, is the shape it makes. So they're the sort of the party animals. Phosphorus ends up with 10 electrons around it, and sulfur ends up with 12, which are exceptions to the octet rule because octet says 8, right? Okay, so going forward, everybody got that down? All right. So going forward, we're going to talk about resonance. And resonance is when we have a hybrid, when we can draw something 2 different ways. And because we can draw it 2 different ways, it actually is in space, in real life, 2 different ways. And when we try and analyze it, we get 1.5 bonds, or we get 1 1/4 bonds. That's because this bond keeps moving around, and because it keeps moving around, when we do tests, it shows it's here one time, here one time, here another time. So it moves, and it gives us a fraction, which we know we can't have. But this resonance, being able to move that double bond around, actually helps it be more stable by spreading out the lone pairs and electron pairs and multiple bonds. And we call this resonance stabilized structures. Yes?
What is, can you I think I know, but what is lone pairs again?
Lone pairs are 2 electrons that are not shared in a bond.
Okay.
So they're like if I had the nitrogen here with a 2 up here and I had it bound to hydrogen all the way around, these right here would be the lone pairs. The ghosts, yeah. The electron, if it just says electron pairs, it's just like fluorine. It has 3 sets of electron pairs and 1 that would be shared with something. Okay? Good questions. Okay? Trying to keep this up down here too, and it keeps going to nothing. All right, so going forward, we need to be able to draw resonance structures, and they're not that easy. So I'm going to take you through the process like I would do it if I had no idea how to draw a molecule that I was given. Okay? So the first thing I do is say, okay, what molecules do I have? Well, I have hydrogen. I know hydrogen has 1 dot. And then I have carbon, and I always use different colors. So you got lots of different colors of pencils here, so pick another color for carbon. And it has 4 around it. And then I have oxygen, and I have 3 oxygens. So I do go ahead and draw 3 oxygens with all their little things around them. And I say, okay, at this point, I need to be able to put all of these together in some form so that all of them have 8 and hydrogen has 2, because that's the exception to the rule for the octet, right? But carbon needs 8, oxygens need 8. And there's only one carbon as far as what can have more things bound around it. Oxygen's closer to fluorine, so it's not going to like lots of things bound around it. So I'm going to put carbon in the center, just thinking out loud, okay? So I'm going to put carbon in the center, and I'm going to probably have to erase this a couple times, but that's okay. So make a couple places that you don't use up all your space. And I say, okay, I know oxygen needs 2, right? So if I put 1 oxygen in and grab 2 of these blue dots, so I'm going to actually move one of these blue dots over to right here and say I'm going to bring an oxygen in, and it's going to share 2 with that carbon. Okay, I've got 1 oxygen taken care of, and I've taken care of my carbon as far as putting it down on there. Okay, the oxygen's taken care of, but the carbon is not. Now I'm looking at my carbon, and I say, okay, but it only has 2 other electrons, and it needs to share with 2 other things. So I can't use both oxygens unless I give each oxygen 1, but then they're not satisfied. But let's go ahead and put them there. Maybe it'll work. So I'm going to put oxygen here. It's just going to be able to share 1, so it has 1 that's not shared yet. I have another oxygen that's going to go here, and it's going to have 1 extra space too. So now I've used all my oxygens. I have a hydrogen. Well, a hydrogen can fill one of those holes on the oxygen, right? Okay, so I'm going to put a hydrogen right here. It doesn't matter where I put it, just I'm going to put it one place. Oh, and then that negative means I have an extra electron, right? So that extra electron is going to come in right here. Okay, does everything have 8 around it except for hydrogen, which only needs 2? Double check, did I do it right? Now, I did it step by step. I knew hydrogen could be a fill-in at the end because it only needs 1 bond. So I didn't put it on the center one to start with. I could have said, oh, well, let's put hydrogen on the center, but then I'd had to back it out. Okay, so I can draw this with the stick figures. So it looks like this. Carbon, oxygen to a hydrogen, double bound to an oxygen, single bound to an oxygen, but it's in brackets with a negative on it because I added an electron, right? To make a resonance structure of this, I would do this again in brackets, but I would move one of those bonds around. So I could say, oh, what if I took that double bond and put it up top? So I put the double bond up here and move the single bond right here, but still leave the OH down here. So I didn't just turn it in space. I actually made something, I didn't want it, come on. I made something new. Does that make sense? I didn't just turn it in space. I actually made a new compound because these 2 switched places. Does that make sense? So these are resonance structures. I want you to see what you can do with SO2, and this should have been O3, so change that to O3. See if you can figure out how those would go together. SO2 and O3, and how would you make resonance structures with it? I know I probably should have given you a lot more space, I'm sorry. If you have to, use some other piece of paper. I'll start it here in just a minute, but I want to give you a head start and see if you can do it. This is driving me nuts. Sorry. I was trying to figure out what was making the noise. Did you get it? Did you figure it out? It sort of looks the same, like it could spin in space, but it actually is two different things. And you got to think of it just like we did the bottom one. I just switched two things. I didn't turn the molecule like this. Okay, so O is going to be basically the same thing, but it's just O's instead of having an S in the center. Whoops, see, I wanted to put an S after I said S. Oh. Okay. We okay with that? Did you see how I did it? So those are resonance structures. So if we look at O3, which is ozone, and we try and determine what the length of the bonds are, it actually comes out being 1.5 on each side. That's because we see both places where the double bond is. Okay? All right, okay to move forward? Okay. When we talk about health, because this chemistry class is more geared towards those going into health things, we talk about a lot of covalent compounds that are in the body that are important, especially to like the chemistry of the heart. In the chemistry of the heart, we have glycine, which is usually does a building block of the protein that composes the heart muscle. And then we have nitroglycerin, which acts as muscle walls to help the vessels, increasing blood flow and oxygen and delivery to the heart. We have the protein hemoglobin in the red blood cells that binds to O2 to help transport it throughout the body. And then we have the biggest molecule that's covalent, which is water, which is part of all of our body, all the way around. And this picture is actually in your textbook, and you can see it in your Learn Smart and go look at it a little bit more there. But there's a lot more covalent compounds in our bodies, and we use to our bodies to help with getting things around. So if you don't get everything down here, it's okay. I'm going to put this up on Weber, and this page is also in your book, so you can look for that too. So I'm going to go ahead and go forward. We also talk about ozone. We just talked about ozone, and you've probably heard it for 1,000 times since Earth systems. If you did Earth systems or biology, they talk about the ozone hole and what problems it has and why it's growing, and pollutions cause all these problems. And we do have an ozone layer, and ozone is actually a pollutant if it's down on the Earth. So ozone protects us if it's in the layer between the troposphere and the stratosphere, but if it's down on Earth, it is considered a pollutant, because it does cause problems. It's got a radical issue going on there. But it does shield us from the UV rays, and it is covalently bound. Okay, so now we're heading into naming type 3. Now, here's where I put a huge, 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 huge caution. It can only be with 2 elements. And those 2 elements have to be a non-metal and a non-metal, or a non-metal and a metalloid. That's the only things you can use. Okay, the only things that can be in this type of naming. Once kids learn how to name this way, they want to try and name everything this way. So this is my huge caution because we're going to be doing an end of year test, and if you start naming this for everything, it's going to blow bad. Non-metal to non-metal or non-metal to metalloid. This is the only time you can use that. So this is the upper portion of the P. So up here on this side, right here, not including noble gases because noble gases really don't bond. Okay? So when we're using this upper portion of the P, we're actually going to, you already know how to name this. What's CO2? What's the name of CO2? Carbon dioxide. What's the name of CO? Carbon monoxide. What are you doing? You're putting a prefix in front of how many you have. So CO2 is carbon dioxide, C with 2 oxygens. Carbon monoxide was C with 1 oxygen. Notice we only put the mono on the second one though. If we have one of the first, we don't put mono in front of it. So if I gave you N2O5, what would you call it? Dinitrogen what? Pentoxide. We drop the A because the O and the A conflict each other. So make sure you know the prefixes. If you don't know the prefixes, write them down. I don't know if I've got them in your notes or not. I think I just put the numbers, so make sure you've got the names down if you don't know what they are. They're sort of like math, but instead of quad, we use tetra. And I think that's the only different one, right? The others you use in math for the same numbers, right? So our tetra is like Tetris. I just remember Tetris. That's a 4-block thing that goes together. Okay? We good? Okay, so the chemical formula does tell you how many. Here's my big caution again. You can only name compounds where both elements are above that diagonal line in the P. Okay, both elements, and there can only be 2 elements. Okay, on the diagonal or above it. Okay, so we're going to practice. Dinitrogen pentachloride. Just shout it out. What is it? 2 nitrogens with 5 chlorines. P2O5, what's the name? Diphosphorus. For us. Okay, give me the last part. O5 is what? Pent. We drop the A in oxide. If it's not 2 vowels next to each other, then we wouldn't drop the A. Okay. See how fast you can do this. See if you can beat me. Go. I'm going to give you a 5-second head start. Done. Who beat me? Oh, most of you did. I had tried big. Okay, so we're going to go to the next page and go ahead and start writing. I'm going to have you guys put them up. So I'm going to give you a number. Whatever number I give you, you put up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I know 11's not on there, but we got another page. Then you guys will get a second number. Yep. So as soon as you get yours done, you can go ahead and put it up and see if you can beat the last person putting it up by finishing all of them. You do the number you're assigned, put it up on the board, but then hurry quickly and see if you can get 1 through 10 done before everybody gets theirs up. Scary shirt. I don't like clowns. Which one are you having problems with?
You gave me number 2.
So number 2. What's O?
Oh, I don't think I'm not on that one.
Oh, sorry.
I don't know where you guys are at.
Right here.
Oh.
Is this right, or would it be mono?
Nope, that's right. You don't put mono on the first one. Did you see your picture? Weber State sent out their thing for the Science Day. It's up by the check-in desk. You have to check it out. Yes, right. So while they're still writing, keep writing as fast as you can. See if you can beat the last person by getting them all done. So you don't have to copy from up there. Try and do it on your own. See if you can do it by yourself. Try, like a tricycle. Yeah, 3, because there's 3, not 4. Floor.
Yeah, that's right. I spelled that wrong.
You did. Nope, you gave me flour. Don't give me flour, it's fluoride. You first.
So when I try going on the column, what does their snapping?
That's why I wanted to try it to see if it was working or not. I wonder if it says go home, because when I did go home, it did. Okay, let me see what I can do to fix that. I wanted to see if that padlock would work, but evidently it's not working. So, did anybody else try it? Anybody else able to get in? You said the same thing. Okay, I've got to figure out how to use it then. Okay, let's double check. If you're done, then you did well. First one is right. Second one is correct. Third one is correct. Fourth one is okay except for you. Fifth one is right. Sixth one is right. Seventh one is correct. Eighth one is correct. Ninth one is correct. And 10th one is correct. So we're going to go to the next one, because this is where the next group had trouble. So see how fast you can do it. I'm going to give you numbers again. What? Yep. So I'm going to give you numbers again and see where we go. So 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Once you get done, get it up. I didn't. You got off this time. Because we've got 11 kids. Hexa. What? 7 is hepta. And I'm hearing this is so easy, which is awesome, because that will make the test even easier, right?
But this is what our test is on?
Mm-hmm.
Supposed to be for this one, is it monofluorides?
Yes.
Yeah.
Yep. Try and do it on your own as fast as you can before these guys get all done up here. So as soon as you get yours up there, write it down. Or if you're waiting, write them down real fast before you get up there. See if you can beat them. If you finish, go ahead and keep going. These you should be able to do really quickly. They're really easy, straightforward. If you guys are on the other side, if there's 2 things up there, you can write at the same time.
Wait, would this be hepta oxide then?
Yep.
Yeah, it would be hepta. Okay.
Oh, heptoxide. That's fine. No, you dropped the A. You dropped the A.
Did I do the wrong one?
Which one?
Oh wait, no.
I thought I had 13.
Do 19. Did somebody get assigned 19 that's not up here?
I have 14.
Yeah, do 19.
I did.
See if you can get it done fast, guys. Last one's coming up. Hurry, quick, hurry. See if you can beat him. I gave the tallest person the smallest one. He can kneel down and reach the board just fine. Okay. How are we feeling about this? We like it? Pretty easy, right? So 11 is correct, 12 is correct, 13 is correct. Nope, it's not correct. What's wrong with 13?
It should be
Dichlorine. Dichlorine. And that means number 14 is wrong. Why? It's supposed to be chlorine, not chloride. Ide means it's the most negative one, and it's not here. So dichlorine, okay, heptoxide. And then we've got 15 is correct, 16 is correct. Way to remember the mono. 17 is correct, 18 is correct, 19 is correct, and 20 is correct. So how are we feeling? We got this? Okay, I know there's more. I'm going to skip over them. If you'd like to try them later with your partner, you can. Let's go ahead and go on in notes because we've got we got to make it through notes today. Okay, so we're now going to be talking about shapes because when you talk about covalent molecules, you talk about shapes. So there are some shapes that are drawn right underneath here. We want to talk about the angles. So if I'm linear with 3 elements, I'm going to have a 180-degree angle, and it's going to be called linear. If I have 3 things around a center, they're going to stay in the plane, and it's going to be called trigonal planar, and the angles between are going to be 120. If I have 4 things around it, now goes 3D. It now is out of the plane, and it's what we call a tetrahedral. And it sort of makes a pyramidal kind of shape. And the angles are 109.5, and they're all 109.5. Then we get a little bit strange. We take that tetrahedral, instead of attaching something, we put an unshared pair of electrons, or one ghost. And the way I remember this is the unshared pair of electrons, you know, if you draw a little thing around it like this, it looks like a ghost. So it scares down the angle by 2. That's how I remember it. So the angle here becomes 107 degrees, and it's trigonal pyramidal. That center, that nitrogen, because of the unshared pair of electrons, is actually pulled out of the plane, because otherwise it would be flat in the plane. Okay? The next one, this is the one I told you to watch for, because they like to trick. Okay, the way they've drawn it right here looks like it's a linear, right? It is not. You got to remember that it is this shape right here where 2 of them are unshared pairs of electrons and 2 are attached. So the 2 that are attached now, like this, okay, so here's my 2 ghosts, and my 2 ghosts are going to scare down the angle by 2, but what's left is a bent shape, right? It's not linear. So we end up with a bent shape, and it's a 105-degree angle. So be careful. This I'm warning and warning and warning. Be careful on this because they will show it like that, but you need to know it's bent. So that one has unshared pair of electrons. This one does not have any unshared pair of electrons. Okay? The other one has 2 unshared pairs of electrons, so it's going to bend it. Okay? It's going to scare those closer together because you got 2 ghosts scaring things. Okay? All right, so this is the thing that you have. There's a whole bunch of stuff that you need to fill in on this, and I'm just going to talk while you fill it in. So the first one we talked about is linear. You just have 2 things. There's just 2 ways it can go. There's not much about it. The second one is trigonal planar. If you have an unshared pair of electrons on a trigonal planar, you're going to get a bent. Then you have a tetrahedral, and we're talking about the tetrahedral. If it's got 4 things attached, it is a tetrahedral shape. If it has 3 things attached with an unshared pair of electrons, it becomes trigonal pyramidal. If it has 2 things attached with 2 unshared, it becomes bent. Now, these bottom ones, this is our funky ones. This is phosphorus. This is sulfur. These are our PS by the way they get it their way, and they do all kinds of funky stuff. So the biggest ones that you need to know about are the trigonal bipyramidal and the octahedral. But know that it can do the same kind of weird stuff that by adding unshared pair of electrons in there to get other shapes. Okay? And you'll notice that very end one on both of them, if they have two things attached and all the rest are unshared pair of electrons, it becomes linear. Because the unshared pair of electrons will go towards that center paper. Remember how I described it as a paper? They will want to be on the paper because for the trigonal bipyramid, they are 120 degree angles away from everybody else, and they like their space. For the linear, for the octahedral shape, that one you actually turn and flip and flip and flip, and it's all 90 degrees, so it doesn't really matter where it goes. So it wants to have the things that are bound farthest away from each other. Okay? All right, so we're going to practice. See if we can just look now without having to draw the periodic Lewis dots and see if we can figure out what the shape is that these will make and what the angles would be. Okay, so BeCl2. First of all, picture in your head, what's the Lewis dot for Be? Where is Be? It's 2. It's in the second column over. So the one's going to be on one side, one's going to be on the other side, right? So that's where they're going to attach. Right? Okay, so there's 2 valence electrons. There's no lone pairs. What shape is it going to make? Linear. What's the angle? 180. So you got that one right. So now let's look at BCl3. It already tells me there's 3 bonding pairs. There's 3 valence electrons. There's no lone pairs. What shape? The triangle one, right? But it's all going to be in a plane because there's no lone pairs. So trigonal planar, what was the angle on a trigonal planar? 120, good. Okay, so looking at the next one. CH4. So one thing in the center, 4 things attached to it, no lone pairs. Tetrahedral, what was the angle on tetrahedral? 109.5, good. Okay, nitrogen. What does nitrogen look like? Well, I know it's 3 things are attached, but I know nitrogen has 5 in its outer shell, so there's 1 unshared pair of electron, right? That means 1 ghost. What does that ghost do? It pulls nitrogen out of the plane, right? So what shape am I in? Trigonal pyramidal, good. And what was the angle? I got 1 ghost. 107, good. Okay, water. This one we just need to know. It is bent. What is the angle? 105, awesome. So we should be able to just look at a chemical and be able to pull this stuff out, okay, and be able to say, okay, that's the shape, that's the angle. If I have to draw it, okay? Please draw it, especially when it comes to like water. Make sure you put them in going like this for your dots so that you get the shape that it's supposed to be instead of water where they show the 2 up and down and where it's straight, but it's really not. Okay? All right, so now we're going to talk a little bit about electronegativity. Electronegativity is the pull for electrons, how badly it wants electrons, how badly it can get electrons. Fluorine has the highest pull for an electron. On this chart, it's 4.0. Some charts have it as 3.98. Since this is only to 2 significant figures, they rounded it to 4. Okay? Same thing with francium. It's 0.6 something, but they rounded it to 0.7 on this chart. Basically, the closer you get to being a noble gas, the higher the electronegativity. Now, you'll notice on this chart, there's a couple of noble gases that actually have electronegativity. That is unusual. Usually, we just ignore the noble gases because they don't want electrons. Okay, so coming into how do I make it work? When I'm looking at electronegativity, if I take 2 elements and I subtract their electronegativity on a chart, then I can see what kind of bond it's going to be. Is it going to be a purely ionic bond? Then when I subtract them, it's going to be 1.9 or higher. Is it going to be a polar bond where one's a little bit stronger than the other, but it's not quite ionic, but it's not quite covalent? It's going to be between 0.5 and 1.9. That's an unequal, like tug-of-war sharing. If they're both nonpolar, they're both about equally matched, okay, it's going to be below 0.5. So, let's try some. Well, let's look at them first. Water is one of the ones that is really easy to see if it's a polar molecule. So if you saw this symbol in math, what does that mean? It means what? Change, right? We're going to use the lower, the small delta, which is this. It means a slight change. It's not a full change, it's a partial change. And a partial positive. So oxygen tries to pull the electrons from hydrogen, but it's not quite strong enough to do that. And because of that, we get what we call a polar molecule, where I can take with one line and separate the slightly positive side from the slightly negative side. And so we get a polar molecule. Okay? Understand? All right, so let's look a little bit farther here. Look at these molecules, and I've put the partial charges on them for you. So we talked about water already. I know I can split this one. I know this one is polar molecule. What about CO2? Can I split that with one line and get the positive away from the negative? No, I could put a circle around it, but I want one line to split it. So there's no way I can have a positive and negative side of this because the outsides are negative, positives in the center. So this, as a molecule, is nonpolar. The bond is polar, but the molecule is nonpolar. You've got to make sure you make that difference. Okay, if two elements are bound to each other and they're not the same, you're always going to have a polar bond. But overall, as a molecule, do I have a polar molecule? That means, do I have a positive side? Do I have a negative side? So let's look at this one. Can I split this one and get a positive side and negative side? I can, because H's and C here are going to take a positive where the chlorine is going to be the negative. So I can draw a line and I say this is the negative side, this is the positive side. So this one is polar. Well, I've got chlorines in this one too, but it says that one's a nonpolar overall. Why? Well, I could cut one chlorine off. That bond is polar, but the whole molecule, the only thing that's positive is the center area, right? And I can't cut that out with one line. I could cut it out in a circle, but that doesn't make the molecule polar. Okay, yes? Right, I'm just trying to say, can I have a positive side and a negative side of this molecule? If I were to go like this, here's the molecule. Is there a positive side and a negative side? Or is it more like this, where I have a positive and negative all around, or negative and a positive all around? If it's like this, this is nonpolar as a molecule, but this one is polar. Okay? All right, so this is a really awesome FET. We're not going to have enough time to go to it, to play in it, but write this down, the molecule polarity, 2-atom, 3-atom, and real molecule. This is a fun thing just to go in and play. It gets in your head how this polarity thing works, and you've got to be able to have this in your head when you get to the test. Okay, so next time I won't be here. You have time to do your Learn Smarts, your homeworks. This is a thing I would put on there to get in my head what it actually looks like. So all you have to do is go to PHET, P-H-E-T, and then look up molecule polarity and just play it. Just play with it. Okay? All right, so let's try some of these. So let's see if we can figure out if a molecule is going to be ionic, polar covalent, or covalent, just by using the electronegativity from the charts. So lithium, right here, 0.98. So 0.98. And fluorine, right here, 3.98. I subtract them, I get 3.00. Well, that's really ionic, right? As it's a lot higher than 1.7. So this one is ionic. Would you do the other three and see what you get for what kind of bond they are? I'll go and circle where the elements aren't if you don't know where they are. So you can find them fast. And you just take the one that's the highest electronegativity minus the one that's just lower. Okay. What type would copper 2 oxide be? I heard nonpolar, I heard polar. This one is polar covalent. Okay, what about nitrous oxide? Or nitrogen monoxide? Nonpolar. Good. Nonpolar covalent. Okay, and what about HF? That one is ionic. Okay? So if you know what to do, this is really easy, right? But the big thing that you need to remember is where it's dividing. On your book, this is 0.05. A lot of books say 0.4, and yours is 1.7. But it is like an increasing sliding thing. So you're increasing in ionic character or decreasing in ionic character. So just know these are your break points. Here is considered nonpolar covalent. This is polar covalent. This is ionic. Okay? You need to know those breaks. Or put them on your period or on your 3x5 card. Hint. Okay. When you know the polarity of individual bonds, so remember I told you if it's two different elements, it's going to be a polar bond, right? But you've got to look overall, what is my overall polarity of the molecule? The one that's closest to fluorine is always going to be more negative. Okay, so that's going to have the slight negative. The other one that's farther away from fluorine is going to be slight positive. So, nonpolar molecules generally have no polar bonds, and their individual bonds are dipoles that cancel each other. Okay, polar molecules generally have a polar bond, and they have one side that's positive and one side that's negative. Can I help you? Not right this second. Yeah, thank you though. So let's look at these again and just in our head. And this is like the molecule you'd be seeing on that FET at the top here. This is how they sort of colored in your head so you can actually sort of see the positive and negative side, which helps. So remember oxygen, we could split it in half, or water, we could split in half, and there was a negative side and a positive side. What about hydrogen chloride up at the top, which also is known as hydrochloric acid? Is it polar, nonpolar, as a molecule, or as a bond? Or both? What do you think? First of all, bond, polar or nonpolar? Polar. Okay, what about the molecule? Polar or nonpolar? Is there a positive and a negative side? Yeah, there's a positive side right here. This is the positive side. This would be the negative side. So when you see this arrow that goes like this, that means this is the positive side, it heads to the negative. So those are what those arrows mean. So this one is a polar molecule. What about the nitrogen? Are the bonds polar? Yes. Is the molecule polar? Yes. Be careful with this one because if you draw the Lewis dot for this, this is what the Lewis dot looks like, right? And it doesn't look like I can cut nitrogen away. But what you need to remember is this ghost up here pulls nitrogen out of the plane. So he's out of the plane and you can cut him off. So there is a positive and a negative, and this is a polar molecule. What about BF3? Are the bonds polar or nonpolar? Are they different? Yes, so they are polar. What about the molecule? Can I cut B away from the F's? Like this. No, it's all in a flat plane. There's no unshared pair of electrons pulling that B out of the plane, so it stays in the plane. Okay, so I can't pull it away. Okay, carbon tetrachloride. Are the bonds polar? Yes. Is the molecule polar? No, why? I can't cut the C away from the chlorines, right? It's in the middle of the molecule. So that is a nonpolar molecule. Okay, next one over. It's methane, but it's chloromethane. We've replaced a chlorine with one of the hydrogens. Are the bonds polar? Yes. Is the molecule polar? Yes, because this side is my positive side, slightly positive, and this becomes my slightly negative, and I can cut it in half and have a positive and a negative side. Okay? We all right? You look like you're dying. I know. We're almost done. Okay, so now we're talking about how we use covalent compounds. The big thing here is you need to be able to look at a molecule and be able to determine if it is polar bond-wise, if it is polar molecule-wise. Whether or not you know how to name the molecule, whether you know or not you know what in the heck the molecule is. Okay, so hydrogen peroxide looks like this, and it looks like it would probably be what? Polar or nonpolar? Just looking at that part as a molecule. Probably looks like nonpolar, but here's the big but. This is what it looks like as a model. My unshared pair of electrons are down here. That leaves me able to cut it in half, so it is a polar molecule. So we got to be able to not just look at it as a fluorostat, but look at it a little bit more. Okay, here's acetaminophen, which is also a covalent molecule. I've highlighted some things for you here. Oxygens are negative. Nitrogens will probably pull out a little bit negative. Everything else on that molecule is positive. Is that molecule a polar molecule? Does it have a negative side? Does it have a positive side? Does it have a negative side? Does it have a positive side? Think about that for a second. Talk to a neighbor and see if you agree with what they think. Okay, what did we decide? Polar or nonpolar? How many say polar? How many say nonpolar? You're right at nonpolar. Why did you decide nonpolar? Because the negatives are spread around, right? There's really no negative side, positive side. So great job. Okay, let's look at ethanol. This is what ethanol looks like as a Lewis dot. What do you think as a Lewis dot? Talk to your neighbor. You think it's going to be polar or nonpolar? Hydrogens and carbon will be the positive side. Oxygen will be a negative. Hydrogens and carbons are usually considered positive or slightly positive. So talk to a neighbor. What do you think? Polar or nonpolar? Okay, I'm going to give you a little bit more information. Here's what the model looks like. Is there a polar or nonpolar? Raise your hand if you say nonpolar. Raise your hand if you say polar. It is polar. Okay, the reason why is this oxygen right here is sort of out there by itself, and you can sort of isolate it away from the rest of it. Okay? All right, let's look at this one. This is acetaldehyde. Now, if you drink alcohol, which I don't suggest you do, but if you drink alcohol, what happens is you take in ethanol in your body, and your body processes it, and it becomes acetaldehyde, or ethanol. And ethanol is a poison to your body, and that's why you get sick after drinking alcohol. This is what the molecule looks like. Polar or nonpolar? polar. So you need to be able to look at this and say, oh, I know that's going to go off on its own, so I can see it. This, you've got to realize, it's not really straight, right? It is actually bent like water. So as it comes out, it's bent like water. So I'm going to be able to cut that oxygen off. They're going to draw it straight. They're going to draw it straight. So in your head, you need to remember the shapes of how things go together. Okay? All right, so if you drink alcohol, what happens is it oxidizes in your stomach. And as it oxidizes, it becomes acetaldehyde. And acetaldehyde damages liver and brain cells and causes cancer. So that's where the problem lies. Okay, here's another one. This is something you wouldn't know. She could put it on there, just give you the structure, and say, is there a negative and a positive side? This one's a little bit harder. What do you think, guys? Polar or non-polar? I'm going to make you make a decision. This one is actually polar. The reason why, look, I have a negative here, negative here, negative here, negative here, right? I also have a negative here and a negative here. Nitrogen is getting close to the carbon. It's not as negative as the others, so I really can't count it. So basically, this side's negative, that side's positive. You see it? Because I have so many oxygens on the upside of that molecule, that side has more negative. Because oxygen's right next to fluorine, right? It's more electronegative than nitrogen. So it's going to pull the electrons to that side. Okay, so that's the end. So you just sort of need to be able to visualize things and do that. Now, let me talk about what's going down. Friday, I need you to do your pre-lab for the lab that we're going to do on Tuesday. Books are there. You're welcome to get that part done. It's just that front page. This lab is pretty straightforward. It had a lot of drawing in it. I was not going to redo the procedure for you. You can follow it. It's okay. So look through it and sort of see what you need to do. We are going to be working with heavy metals that day. So because we're working with heavy metals, we will be using gloves. Okay? So sort of look through the procedure, see about what you need to do. You do need to have a pencil for that day. Okay? Because we are doing chromatography and separations. Friday, you're also going to be working on all your Learn Smarts and your homeworks. You've got to get them done that day. Okay, you have to get them done that day. So if you need to work on a few before that or after that, get them done. When I see you Tuesday, they need to be done. Okay, I'm going to have you report to me on Tuesday through a Nearpod or whatever to get results from you to see where you're at. Okay, I want everybody done then so that we can answer any questions you have on Thursday when we come to class as a review, because Monday's your test. So Monday, November 12th. This is a short chapter, very short, but it's not really hard. I hope you think it's not very hard. Okay, so we're going to go over things. Remember that the review is on the back page, so sort of look over that review. Make sure of what things you might need help on following Thursday. Okay, questions? Okay, you guys have 20 minutes to either work on your pre-lab, get it done, or work on a Learn Smart, get it done. Whatever you want to get done, but get something done. Okay? All right. And if you want another pretzel, you're more than welcome.